Okay, opportunity, but my main task or aim is to give us presentation of work in progress. So let's say we can discuss a little bit more also on the details. And as Camille asked, so it is, I would like to try to keep it as general as possible, or at least to understood to broad audience. So first, I will start with overview. Then I will focus on the specific oscillator design. It's a Colpitts, and we'll try to give it as clean as possible, the basics, the operation at high frequencies and its implementation, and then about layouts and results. So first, Greg, could you tell, is it okay now? Do you see it properly, the presentation? So are we at the third transparency?
Yes, we can see slides without logotypes.
Okay. Yeah, sure. There are no logotypes. I don't know what happens. Somehow it is animation mode, and I have to cross-check. So first, can silicon actually to be discussed at all as a high-frequency material system? And for this, there is a recent review. I'm sorry, just a noise. I have this. Okay, now it's better. WebEx covering me titles. So first, if you have seen review of Bozanic and Sinha, then, for example, that's a consensus that development technologies are actually the best technologies are indium phosphide or 3,5 material system, and those are either HEMT or HBTs in 3,5. And if we would see where silicon is, then there is definitely RF, SOI, CMOS, and there is no standard CMOS. Technically, one would really report about SIGE, HBT or bi-CMOS material, but it's a bipolar. It's in any way circuits based on bipolar concepts. So standard CMOS is not even discussed to be terahertz material. And yet if you, 1 second, what's happening? Yes, and yet if we would just look into evolution of standard CMOS technologies and would just look where is its cutoff frequencies. So one can, well, on the x-axis here is inverse length of the technology, just to show how the cutoff frequency increases with improved node. And 65, we are already above 200 gigahertz. And with 10 nanometers, we are really in 400 gigahertz frequency range. And Fmax is even higher than those frequencies. So actually one message that the drastical improvement of technologies allowed to, even for CMOS, for standard CMOS, to enter fully into terahertz frequency range. It's not exactly what people with development of new technology would address, but it's also a good practical message. Now, historically, CMOS has been shown to operate at already in the terahertz frequency range. It's already in 2008, and in 2008 there were 2 independent groups reporting about oscillators above that border of 300 gigahertz and using 45 nanometer CMOS. And in that time, for example, this push-push oscillator or in 90 nanometers linear superposition scheme has been used with pretty similar power. It's about minus 47 dBm. So it is below 1 microwatt. Something in sub-microwatt power level. And interesting is that at that time they claimed that actually the simulation and results are in about 1 dB difference. So then that means PDKs or simulation tools, even already in 2008, were very precise in prediction of a performance of something more complex and entering already into terahertz frequency range. Now, since then, there was a lot of, there was development also in topologies, because that push-push appeared to be not the best topology for high-frequency operation. And if in 2011 was a strange paper saying that you can have 65 nanometer CMOS in this specific buffer feedback to oscillate at even 300 gigahertz directly, there came several other concepts like a triple push and differential, actually the triple push, which makes it even more complex, at 280, or for example differential Colpitts also at nearly 300 gigahertz. And those oscillators at the right side differ from the first, that at the left we have, the claim was that this is a fundamental, whereas on the right side we have harmonic oscillators, which work at much lower fundamental, but then harmonic emission. And the state of the art for those technologies is presented here by one of the recent works of Wuppertal group of Ulrich Pfeiffer. And blue color is that of CMOS, and red color is that of SIGE, that's BIMOS. And what we see that in general that's very similar or competitive material. Silicon is competitive, and you can, I'm sorry, somehow I have automated presentation. So that silicon is really entering fully into terahertz frequency range. With powers, dBm is a milliwatt. So actually up to 300 gigahertz there are devices milliwatt or even reaching 10 milliwatt. And nice results with 10 milliwatts is led exactly the power of MMIC technologies, that you can make really matrices of devices. Like here are 30 devices, or let's say we have a point here at 400 gigahertz, there we have 64 devices. I will come to this transparency later in the end of the talk. So just to show you, first message, that silicon is a material also good for terahertz, and one can create a lot of interesting designs. And so, yeah, it's not that competitive as 3.5 on a single level, but nevertheless can create circuits which are in the end as good as what we used to know. Now, one of the important development is a Colpitts oscillator, and therefore I just try to tell you what's the difference, why it is so important. So Colpitts is a single transistor oscillator, and the point is that we have here, if we have a perturbation here, so you know, like single transistor can be used as amplifier in different configurations, and for example, common drain, common source, or common gate configuration. The most important thing is that you have you have one inductor and two capacitors, and with that you can create really a positive feedback loop. And there are actually different configurations like Hartley, Clapp, and Wacker in addition to Colpitts. Sorry, I'm sorry, I have to remove animations because now it goes automatically. But the most important thing is that all that can be easily implemented. And actually, the most important is that Colpitts oscillator, which I would like to go now into detail in this common gate configuration. This is something which is the winner configuration right now. And so from that, I would like now to go slightly more into physics, what is behind or how it is really working. And so first, if we take AC equivalent of transistor, that would be the simplest one, is that it is just a source with GM. So there are no parasitics yet here. And we add all those three elements. LD, capacitors, C1 and C2 here as dividers. And then we would take just Kirchhoff's laws and calculate currents. So Kirchhoff's current law here at the node of the drain terminal. And we have also at the input another current law here. So just calculate directly transfer function. Now then this transfer function, let's investigate the denominator of it. And yes, again, that's a transfer function. And let's look into denominator, and we check then it is approaching to zero, to condition for oscillations here. And so it is easy to find out for the imaginary part, it is zero only then those elements allow us to get zero. And that's actually resonant frequency, just a parallel connection of C, those two capacitors, multiplied by inductor. So simple as that. Now, the real part would say, what gain do we need to get? And actually, that's a weak part of Colpitts in this case, because it requires gain more than 4 to get active. And that's why push-push actually was always considered to be better, because it requires less gain per transistor. But the point, at high frequencies come additional 2 capacitors here. Gate is shunted directly to source or to drain. And now if we take all those capacitances, and actually one capacitance is already inevitable, drain to source capacitance belongs directly to transistor. So it's also one parasitic, not directly considered. Now if we take those 2 capacitances, actually we would do the same analysis. That's also additional shunting here by capacitor, but actually it's just capacitor action, nothing more. What helps is to add inductor at the gate. If one now adds inductor, so the shunting role of C gate source actually gets eliminated to some extent. This inductor here also adds a little bit, well, it adds directly to drain, but well, the action is different. So at one point it just sums directly drain and gate inductors into one, and there is so single operation also of drain inductor. But what comes out, that even the gain right now, what you need for single stage amplifier is much lower than that 4. So actually adding inductor at the gate improves the circuit a lot. And one more thing, that's always like in push-push, there are 2 transistors, and that's also one of the clue why it requires less gain. The same works also for Colpitts oscillators one can make. At high frequencies, one can easily make differential configurations. And for example, so if we have now a single configuration here, we can make a mirror action here by a gate, and that would be differential configuration. Now, actually, about capacitors, that CGS and CDS, they are not necessarily needed because they belong to standard transistor. So this circuit requires only drain inductor, inductor at the gate, this is important also, and one capacitor, this is C2. This is only one real capacitor one needs to implement. And there is one thing which makes also a bit interesting, that actually in this case you can have sort of dual operation, because you have both common gate and common drain configuration, and that's a different positive feedback loops in the gain. So to some extent, if one designs not properly, they can compete, or they can add. So actually this is something where a little bit of art is needed. So the final design again is simple. We need a third inductor. It's at the source side, because what we have to do is to ensure that we have ground, DC ground at the source. And now actually we don't need any others except of this CS and in differential configuration, because that's one key. And let's say main oscillator is parasitic of drain source capacitance. This is intrinsic parasitic, and then additional external capacitor here. So actually that's a pretty simple way to create Colpitts. And there is one more thing, that it's not a single oscillator now, but we have inevitably a pair of oscillators, so that actually 2 oscillators can add. They can be detuned slightly to increase bandwidth of the total system. And the power of individual oscillators is summed already here at this. And actually this also allows to get oscillation condition with lower gain than for classical Colpitts 1 transistor scheme. Now I would like to come to a point, I'm sorry, here, about challenges. So transistor topology is simple. Now another thing is, not transistor, oscillator topology is a simple thing. Now, what is the transistor topology? And this is where challenge comes. So we have here now idealized transistor at the very beginning. And if we look now, the same transistor, same 16 micrometer width transistor can be implemented in many ways. One, for example, here can be more fingers, more fingers, and only a shorter length of it. or less fingers but a longer transistor in the end. If we do one or another, we get actually very different frequency behavior. For example, Fmax of the left side transistor is only 144 and Ft is 178. And now if you take a top side, actually Fmax is lower than Ft. That's one thing one has to see at the left side, and the top side, Ft is lower than Fmax. So one can get different, really high frequency performance of transistor, and this is another part of art when one designs high frequency oscillators here. And you know that in the very beginning I showed that Ft for this transistor can be at about 200 gigahertz, yet it's only if you take single small finger. Now, when we do oscillators, we have to make power matching. So we have to extract the power, impedances should work. And so practical impedance, for example, here is for device with really long gate width. And therefore, the price that we pay due to additional capacitance that Ft of this technology transistors really gets lower. But nevertheless, it allows to make a fundamental oscillator below 100 gigahertz here in any in different configuration. So this is one point of art in addition to circuitry, not circuitry, but to topology, circuit topology of oscillator. Now, another part where there is really interesting challenge and also work for physicists is which model to take. And I would like to outline you digital versus RF model difference. So the same transistor provided from foundry has two modalities. One is digital modality if you do it just for digital logic, and one is RF. Now for detector, there is no visible, if we work on detector, so the device is unbiased in the channel, there is no difference between one or another model if we look on its channel impedance. Now, if we look on the GM, there is also almost no difference. This is at the left side. Now, if we would look at the real part of channel impedance, real and imaginary part, and for two different transistors, we see they differ slightly, but I would say, who cares? If that difference is so important. And the question is serious because, for example, if we look into Ft of those transistors, that's black lines here, they do not differ that much. It's only Fmax differs actually a lot. If for RF transistor, we know very clearly that we can have here up to 160 gigahertz only. Then we take digital transistor, we can make it also oscillating up to 800 gigahertz. So that a tiny difference between one or another makes a very huge difference in the design of power oscillator, which would create power. And that's something where hand waving is dangerous, or one has to do a lot of work in addition to check which model to trust or how far one can trust models. Because even on the, as I showed here, on the impedance level, there is not very big difference between one or another. There is slightly more slightly more impedance at the real part of the gate, but it's on the frequency, and there is the difference actually becomes minimum here. And yet there is a crucial change here in what we will have for Fmax. Now, having this, we just would like to show that over time, there were a lot of oscillators implemented with different elements here, and the topology, that is the schematic, the way how it gets implemented into final device can be very different. So, for example, here we have very clearly defined two inductors at the left side, two inductors, and there is a capacitor in between, and there is antenna for drain inductor plus drain inductor plus antenna for third harmonic generation. And for example, here one can do it also very separately, but use another type of antenna at the bottom transparency here. You see pretty clearly that there is inductor, and then on top of this inductor, additional metals have been added here to emit at third harmonics at higher frequencies. And the nicest one is where the whole transistor is really hidden into the central point. and it has one of the best emission properties from all our devices. And at the right side here, we have fundamental oscillator in IHP technology, where actually the antenna works both as inductor and emitting element. So for CMOS devices, those were kind of separated. For low frequency, it had to be inductor, and it has good dipole moment only for third harmonic. Whereas for fundamental oscillator, one has to combine both induction and also dipole moment into one frequency point. But otherwise, one can use also not necessarily field effect transistors, but one can use bipolar transistors for same Colpitts design and actually pretty similar outer appearance of the circuit. Now let's go slow to the first point. That's the very first design I did. And at this time, I just was not very sure how well should I do antennas. And there is a long here path from oscillator to the emitting part. So there is this transmission line, the long transmission line from one center to another. And this is actually, it's lossy. And what in the end, it resulted to power something like about 3 microwatts. And approximately the same power has been measured. And pretty similar frequency performance has been measured. So at this time, it's RF model used. No question about digital one, and we just trust high frequency models. Now, optimized device. Now everything is put directly in the center, radiation center of antenna. We expect about 100 microwatts and frequencies, good frequency tunability from 260 to 250. And this is what we get. Actually, experimentally, we have about 80 microwatts emission here. And frequency tunability is pretty similar, and just 5 gigahertz offset. So we get actually higher frequency, oscillation frequency than we modeled. So there is small discrepancy between RF simulation of antenna or inductor elements, but that's pretty nicely hitting to the point. Now, on the frequency content here, so fundamental oscillator is at 87 gigahertz. Oh, sorry, fundamental oscillator is at 87 gigahertz. We have second harmonic component, and actually emission really is extracted at the third harmonic. Very interesting that we have also a sixth harmonic in addition with pretty considerable power, just 20 times lower. So it still would be a practical power emission that we are looking, we try now to investigate this higher frequency range in more detail. Now, the SIGA oscillators, so this is how a chip looks like, our first chip. By now we have already a second chip in production. So we have here at the top oscillator for 300 gigahertz, 260, and the bottom at the left side, 200 gigahertz. And actually at 265 that we get emission here, we have more than 300 microwatts emission and about 500 microwatts emission at 200 gigahertz. This is just single spot, pretty good emission. Now, since it's fundamental oscillator, and there is a difference in higher harmonic content, because actually this fundamental oscillator is extremely clean, showing fundamental emission here. That's an oscillator. It's actually the same Colpitts here. It's only field effect transistors have been exchanged by bipolar transistors. So pretty simple design. And by now, actually FBH and many other teams are shifting from the classical textbook push-push into Colpitts configuration. It seems to be really the winning configuration at the highest frequencies. There's still art left in a way how one implements high frequency components. And as you see here, one can do in many different ways. So where we are with that, I would like to show you the same graph that I started in the very beginning. That's 0 dBm, it's a milliwatt and higher. So just to show you the points, the blue points are CMOS and red are SIGA. So the highest blue point here is 30 oscillators made in parallel at once and actually frequency locked. Now, Ulrich Pfeiffer has 64 oscillators, and that's a record value. It's more than 10 dBm, so more than 10 milliwatts at 420 gigahertz using SIGE. And for example, MIT group, I think they have 91 Colpitts oscillator here and have oscillation at 1 terahertz. So this is how you get to the power. Now, our data, you know those points, I already showed them, they are humble. So CMOS is something like minus 10 dBm, approaching to there, and this is what we will get, I think, soon. Now SIGE is in a half of a milliwatt. We are still here at the first harmonic. I think we will compete more if we would go to 500 gigahertz, just 20 times less, then it will be more competitive. But one big comment here, we do single pair analog devices. Now compared to this conglomerates of those devices, the point is that our radiation propagates really meters, and this is nice beam profile and very good for practical implementations. I will not go to that, but you have seen a lot presentations from Dmitro on imaging, and so we have really dynamics, but is really practical on even those single sources. In the meantime, Cesare submitted design where we have 6 sources altogether in CMOS, so we hope with those 6 sources to reach the level of competitors. And I know with Frankfurt we are talking about really big arrays of devices. That's a lot of funding needed to get to those implementations. So this is where we are. Maybe not yet in a worldwide competition, not the highest, but I think it's a good basis to get to practical devices. Now, about multiple devices and strategies, the ideas of combining or to exploit the property of silicon is that one can create conglomerates of devices have been started from very beginning. And for example, Afshari, I don't know exactly where he is now, but that's US concepts have been pushed since 2012. There are a lot of devices are connected here into central point as an output. Ulrich Pfeiffer, chips already 2013. His, for example, oscillator, one antenna is connected from differential triple push oscillators. So that's at least 6 oscillators. That's 3 times more than we have. And this explains right now why our power levels are not that high on one side, but the simplicity of the circuit is also on the other side. It's a lot more like advantage for us. The winning solutions right now on the power assembly is right now here, like Colpitts, the electric resonant antenna there. Not antenna makes a resonance at all, but the whole crystal makes a resonance. And I would give a comment. That's extremely dangerous because that will depend really on how crystals are cut. So it's good for Zoha group to get or claim highest results. In practical, I'm still a bit doubtful about the general concept. Where I do not have doubts, where the antennas are coupled here with slot coupling, so it's electromagnetically, and this is this 91 antenna design by Han Group. I think that's MIT. So this is the direction to go further. Okay, this is where I would like to end the talk, just to thank for you for attention, and if there are some questions, I'm happy to get a live discussion.
Thank you, Alvidas. Wojtek is still with us. Wojtek, we don't hear you. If not, Sergey wants to ask something. Huh?
Yeah. I have a couple very simple questions. Alvidas,
Yes.
The first, when you have a few tens of transistors or generators, are they synchronized?
Sergey, this is exactly the open question. This is where I think to submit now, not Opus Lab, but Unisono project on that, on synchronization of sources. No, they are not synchronized, and synchronization is right now an open issue.
Okay, so it would be nice even if you be able to change the phase individually for each transistor.
Yes, so this is an open issue right now. The point is that I showed you in the very beginning that why one of the oscillators, the very first oscillator, was not that efficient as others is exactly that at high frequencies there is a huge, tremendous loss on the standard transmission lines. So this is where a combination of photonic, micro machining, what Stockholm is doing, or right now Frankfurt really wants to make metamaterial, meta surfaces for this phase synchronization issues, to implement them. So that the hybrid concepts. Directly, it's not working at those frequencies.
Alvidas, I have a question. I understand that this design could be very fast. It means in terms of electrical modulation.
Yes.
Can you say a few words how fast you can make modulation, electrical modulation with such?
Well, right now my experiments are up to 100 megahertz.
Okay.
And then I do not have electronics to test further.
Yes, this is always this is a issue. Yeah.
Yes, so actually that circuit what we have and then Metro uses is up to 100 megahertz. You can modulate it as fast.
But if you will be so rich or you will have access for the equipment, do you have any estimation how fast you can modulate?
Actually, I did some simulations. I know that, this is self-starting oscillator. So if we just run from non-oscillation up to oscillations until self-start, it happens at the range of few gigahertz. Now, the point is that if you modulate between two amplitudes, if you do amplitude quadrature modulation or other schemes, you can get even faster. So this is now actually a realm of communication people, and technically I think 10 gigabit is doable.
No, this is the main point, that how far we can go for communication, because
well, Ulrich does 12 gigabit per point.
12.
Yep.
Mm-hmm. In the two-level modulation.
He has 16 level AQM.
16 level AQM.
Yep, 16 point. Amplitude quadrature modulation scheme. So he actually claims 100 gigabit from because he uses two phases, two phases, and fundamentally he modulates 12 gigabit, but then he goes I remember 4 AQM, so he actually gets to 48 gigabit because he has 4 levels. And then says 2 polarizations. This is how he claims having 100 gigabit.
And my question is, I understand that he is a big elephant with the big money and whatever, just going forward in this communication domain. But are there any chances that we try to go to this direction, even if they much moderate the results? Because people from Poland and from other organizations try to contact us asking about possibility to do anything in the communication with our systems. What is your feeling?
Well, my feeling is very positive, Wojciech. I think, well, it is a lot of effort because we talk about electronics and, I do have extremely good colleagues. If Czarek or Leham listens, or Bramsky, for example, they are good colleagues, but they do close to nothing in practical point.
Okay, So
this is something where someone should be like Dmitro Buter, hands totally always in circuit from morning to the night. And then I am very positive we can get into business. So we need a person who is really determined and he has full support, that he's not waiting a magic list to happen in the next half of a year, probably.
And
but that's a general thing. Kamil would agree with the same with his components. So that's the same issue. But with electronics, it is even more that you cannot really design. You do not know how your circuit will react. So probably you designed it, it is crap, and you have to redesign everything. You cannot simulate everything. Like, for example, how elements would heat or capacities parasitic will happen. And actually, I see one way. You solder it, you test it, and you go with improved designs. It's not like you wait half a year and then.
Yeah, but do you think you need extra manpower to go to this communication, or can you find any new people that could join us with competence?
Well, well, 1 second. I have Czarek and I have Elham. I think what I need to give is to provide them possibility to act.
Okay.
So it's not yet another person. I think this is what we discussed a few weeks ago. I think we have skilled people.
Okay.
Enough of skilled people.
Okay, very good. I like.
We just need to provide them that opportunity to work.
So for the communication, there are two parts. One, to have this oscillator that can be modulated fast enough, and then we need a easier task, but then not so easy, a detector that is with the amplifier that has a flat amplification characteristics from 0 to up to 10 or 20 gigahertz. So on the detector side, it's also the work to do.
Yes, we do not have those amplifiers yet, but I think that the starting activity of Czarek is pretty good. So what right now he implemented, well, we focus on low noise part. But if we would focus on high bandwidth, this comes on the price of noise. But actually for Czarek, it is also a simple task. It only has to be formulated,
And very good. So I'm not insisting in starting it right now, but what I'm going to tell you, and I'm asking you, will be writing a kind of business plan for the money, and also will be writing the next part or the application for the next run of Centera. And having there a part of activity devoted to communication is very important for success.
I think communication is very feasible, and it is very feasible on one side. But there are practical things like we have an oscillator. We have to find out how to stabilize or synchronize it. And this is where I would say a dedicated person has to put his whole time. It's not like we do with Dmitro just on occasion. Okay. So that's, yes, one needs another person on communication.
Okay, so you want to somebody from your group goes there, or you want to get one postdoc more or one engineer more?
No, but I would say, well, first, but the bad part of it, if this person is inactive, then
okay.
So well,
think it over. For the moment, I would not push on yet
another person. I would push on effective usage of funds that we have.
Okay, very good. So please keep in mind that I will ask you at least formulate the dreams for the future for going to communication. In the near future, that means in the next month or two. And we will really need it to have a minimum guarantee for success of renewing our project. Or prolongation of our project behind 2023. And this should be done
but Wojciech, we can do through cooperators, through colleagues. but the equipment, even for this high frequency characterization, is not existent in our case. So that's.
I should know what you need, what is the list of the things, and then we have to take together a decision whether we put this equipment on the list of what we buy now, or we apply for this business plan that should be on the table end of January.
Okay, I'll ask my team to help. First of all, I would like to get my co-workers to contribute to this wish list. So.
Yes, please do. And if we need to contact any communication institute in Poland.
Well, we have Lille, but due to pandemic situation, I never visit them. This is something which is on my list of wish list. I would like to go to visit the Cornell, for example. Why not?
Yeah, this is the best thing you can do. And please do it as soon as possible, because now the borders are open, even if the second or fourth wave, if you have a double or triple injection, then you can travel and visit people. Make at least, if you do not want to travel, then make a Skype conference with him to tell what are his dreams and whatever. This collaboration should be reactivated as soon as possible. This is extremely important, and I would like we have a first signs of this reinitialization of this communication before the December 14, before this meeting with the experts. They will surely ask, what about collaboration with VMN? And I really would like to be able to say, yes, we go for communication with them. Can you please try it?
Okay, so yes, I will send an email to him.
Yeah. Thank you very much. Good. That's all from me, from questions. So I open the way for other people to ask. If no questions, thank you very much for this presentation, and we come back to very good habitude to have these seminars and information on the activity available for the wider public. Thank you very much, Alvidas, for this. For this. Can these slides be available for other people? Can you send